Hi everyone and welcome back to the series about the Swiss bracket. In this video, I'm presenting the expected matching approach, which is the result of a research um, of trying to improve the major, the Counter-Strike major. You can find all my work on GitHub, and there are notebooks to download, and we'll dig into my work. So my work started also from this example, but I didn't really care and still do not really care that the fact, strictly speaking, the fact that the seed 8 does not qualify and instead seed 11 that qualify, this is not something that, strictly speaking, bothered me. But there's something more deep in that picture that caught my attention. And to explain it, I will go to this page on Wikipedia, which is about complete bipartite graph. So this comes from graph theory. Graph theory is that's a graph. Those little drawing are graphs. Graph theory is a field of mathematics that is very useful to solve problem of scheduling, like for example a school schedule or a tournament pairing system. Complete bipartite graph is a specific type of graph or a family of graph, and they have many properties that are studied and very useful, especially for tournament matching. And one of these property, this one, a complete bipartite graph KNN, has a proper n-edge coloring. This property caught my attention, or more exactly, the example caught my attention due to this property. So I'm going to show you what it means. So I'm going to draw KNN. KNN basically is a graph that means this. You have 6 teams, and you have 3 top seed. Those are the top, and those are the bottom. And you want to play game, but you only want to play game top versus bottom. And you played all such game. So for example, Ents will face Monte, Astralis, G2, and it's not going to face anyone from Vitality because those are also top teams. So now Vitality, a top team, will face Monte, Astralis, G2. And finally, the same for X9, Monte, Astralis, G2. That's a graph that we call K3, 3. You have 3 top team, 3 bottom team, and K for, it's German, complete, because you play every possible game that respect this 3-3 structure. Now, the second part of the proposition is as a proper n-edge coloring. So there is the word coloring. Let's use color. A coloring, you color edges. There is a rule. You put color on an edge on a game, and then if you want to add another one of the color, it cannot touch. So I cannot draw this one with red because then it touches here. So I can draw this with red and this with red. Okay, I'll switch color. I will do green here, and I will put blue here. This is proper n-edge coloring with n equal 3. Now, what does he have to do with this example? Well, basically, we just played a tournament. In red, we have round 1. In green, we have round 2. In blue, we have round 3. So if you have 6 teams and you want top and bottom, you can organize 3 rounds where every team faces the other half. And in the example, those 6 teams, they play here against each other, they play here against each other, and they play here against each other in round 1, 3, 5 on 3 occasions. So theoretically, you should not have a fairness issue. You should not have Vitality versus X9 because they are from the same. See, they are from the same family. So this is the problem that caught my attention. It appears that the tournament under the example violates mathematical properties. Now, if you're paying very carefully and you're understanding and you see what I mean, you will maybe point out to me that Yes, we have 6 team here, but here we have 8, and here we have 8. Yes, that's true. And that means we are dealing with K 4, 4, and this means we can play 4 rounds. So what's going on? Well, I will show you what's going on. In the first round, in the tournament, they played this game, okay? And in the second round, they played this game at the major. And that's it. That's the problem. I mean, you may not see it. It's subtle, but there is already a problem. I could continue. It's possible to do like let me just. So round 3, you will do something like this here, and in round 4, and we'll play G2. But I will keep the picture clean. Why is there already a problem? Let me remove that. Let me put this graph next to it. Let me put this graph here. And you can pause the video and see the problem and try to see the problem for yourself. It's actually quite simple when you see it. And okay, I will tell you. The problem is, look at Vitality Astralis G29. You see this pattern? Red, green, red, green. It uses 2 color. But here, red, blue, red, green, it uses 3 color. And when I saw that, when I realized that, it sounds like a teeny detail, irrelevant detail. It's actually core. It's crucial. It's the reason why there is a problem of fairness in the major. When I saw that, I've built 2 algorithms. I've built a pairing system that creates such pattern, and I create a pairing system that avoids such pattern. So um, let me show you how to avoid it is actually very simple. You just instead once you have done that, instead of playing that, you do that, and then you do that, and then you do that. And if you want to play more, you keep rotating. So the third round of ends, you went down. This will be here. And IP, still you don't go there, you go down. This one, you move it here, and you move that here. And finally, you play it in the third round. The last one that has not been played, which is this, I guess this, and I guess this. And this is a proportional K44. I've built an algorithm that generates this instead of the current major system. It creates way more system. I have created 12 different pairing system, 6 that have this problematic pattern, and 6 that attempt to avoid it. And I have built a table that summarizes. You can check all my work, explanation of the algorithm, testing, nice colors everywhere, specification of scenarios. It's quite heavy. I don't want to bombard you with too much crazy, weird, abstract information, but if you go down to this coloring notebook, you will find this table. So what is this table? This table, each row is one of the, I gave them name. So this is actually F1 rotation. This one here, you see it, is the F1 rot 01. I know it, you can have fun trying to figure out the naming convention, but so each row is a different pairing system. They are grouped by family. So F1 rot is a family. There are 1, 2, 3, 4, 5, 6 different versions of this family. Each column is a tournament situation. It tells you which team have been qualified and eliminated. For example, 3, 6 is our situation. You just have to write 1, 2, 3, 4, 5, 6, 7, 8. I apologize. Our situation is oh, there is an error here. Tick, tick. So our situation is 3, 7. So we are in this situation, right? And so if you use the F1 rotation algorithm and you say NIP and Eternal Fire are qualified eliminated, it tells you that that number 4 is available. Number 4, it's basically Valve's priority list. It tells you that the matching 1, 5, 2, 4, 3, 6, which is, as you can see, a fair pairing, is available. So you can check the table. It's called the expected matching approach because you know in advance, thanks to this table, which pairing is available for the last round. It helps you decide. For example, you can, before running a tournament, you can say, okay, oh, I like this. In the last round, I have the best pairing available. So if you want to use it, it's F1 rot 2 3, and I have an algorithm that creates for you the pairing during the major. And okay, you have not always the best option, but once in a while you have the fifth, which is still a fair pairing. It's still the high seed 1, 2, 3 versus bottom 4, 5, 6. Now I want to add something more. So I've run this table, I've completed the values. I know it's a bit abstract. It's supposed to be technical for people running a tournament and who have a little bit of understanding and are used to manipulate numbers. But I want to show you something. The major, the major, the weights played, it corresponds to F1 cross 0, 1, which if you go to the column 3, 7, no, wait. Ah, yeah. Tac, tac. So we were indeed in 3, 6. Okay. Yeah. You see, I've got the problem. It's actually 3, 6. We're in the scenario 3, 6. You have to 5, 6, 7, 8, 9, 10. Yeah, it's 3, 6. If you go to F1 rot 0, 1, which is the major, no, F1 cross, my god. F1 cross 0, 1. You go to the 3, 6 scenario, this column. There are no options. You have to play an unfair pairing. You cannot play one of the 6 fair pairs. There is no valid option. And you know what's really funny? The new rules of the major, the one with the speed up rules, it corresponds to the F1 cross 03. And what's really hilarious, it has the same problematic scenario. Not all the time. For example, here it's a problem in the new system that there wasn't, and here is a problem that was before and is not a problem anymore. But there are plenty scenarios and situations that are identical. They are insanely close in terms of what they do structurally in a tournament. Okay, so I know it was a quite theoretical, abstract, hard video. The more important takeaway of this video is that if you want to play fair tournaments, you need to use 3 color for that pattern, and that the major only uses 2 in this cross. Let me draw it again so that you have the picture of the problematic situation with the solution right next to them. This, ladies and gentlemen, is bad. This is good. You want 3 colors. Okay, see you in the next video. In the next video, I will run a gigantic simulation and test different pairing system to show different statistics about the quality of the tournament. Like, for example, the percentage of top 8 team that qualifies with regarding the pairing. Thank you very much. Hopefully you learned something. Bye bye.